today, and Rahul Ilango will tell us about some really cool and surprising applications of I/O.
All right, so thank you very much. So I'll be talking about some applications of obfuscation and related notions, and so this is based on 3 different works with many excellent collaborators. So the title of this talk is Tales of Obfuscation, but really, for me, the title of this talk is different. The title of the talk for me is Why I Stopped Worrying and Learned to Love Obfustopia. So, and hopefully, I'm sure many people already love Obfustopia. Maybe I can convince maybe more of you that the Obfustopia is the world. Okay, so what do I want to talk about in this talk? I want to tell you about how to apply obfuscation, some recent results about using obfuscation in various areas of theoretical computer science. Now, in particular, there's going to be kind of 5 questions in each one of in these areas that I'm going to talk about how you can solve some open questions using obfuscation. And for now, let's not worry about what the questions are, but we'll see them later. Differential privacy, derandomization, logic or bounded arithmetic, average case complexity, and metacomplexity. And so when I was preparing this talk, I was kind of thinking to myself, okay, what's my goal? What do I want you guys to take away from this talk? And so in The Lion King, Pumbaa talks to Simba, and he says, these 2 words will solve all your problems, or at least this is what people think he said. But if you listen really closely, the 2 words that will solve your problems is actually indistinguishability obfuscation. You got to listen closely. 1994, so this actually predates Barack at all. And so this will solve all your math problems, indistinguishability obfuscation. Oh, yeah.
Can you sing the song with the correct words?
So, karaoke night is, there's a karaoke event tomorrow, Thursday, 7 p.m. I think Stefan is organizing it. I don't know if he's here. You should all come, and if there's demand, I will sing it for you. Actually, yeah, what is it? There's also a line in here that's like in the song. It's a problem-free philosophy. So that, yes, that's the pure philosophy. So my goal for the complexity theorists, at least, or people who are not cryptographers, you have a problem. At least think, whether indistinguishability obfuscation will be able to solve it. I think this is a good takeaway. On the other hand, I guess cryptographers have realized this for a decade now. You have a problem, you can solve it with indistinguishability obfuscation. For you guys, oh, I guess it's a little bit cut off. Oh, I see. Okay, good. My goal is, disclaimer, I'm not gonna give you like fully formal theorem statements, and some things I'm not even gonna like fully define. My goal is to convey to you, okay, what are these questions that are being answered with obfuscation? And I really want to give you like 2 ideas, 2 nuggets that I think might be useful somewhere else, and hopefully that you will enjoy. So that's my goal for the talk. So let's start. And to start off, I want to talk about uses of obfuscation in logic and derandomization, and also a little bit of applications in combinatorics. And so to do this, I'm going to have to give you some background on some of the problems and questions in this area. And then at the end of that, I'll recap what these questions are before I tell you what obfuscation says about them. So the first thing is about this problem called range avoidance, which is a really nice problem introduced by Kleinberg, Korten, Mitropolsky, and Papadimitriou. They were interested in total function problems in the polynomial hierarchy. So the problem is as follows. It's very natural. I hand you a circuit, and this is a big length expanding circuit. It maps n bits to n to the 100 bits. Actually, the n to the 100 here isn't so important. It needs to be some larger than n. Kind of the most interesting case is large polynomial in n. So it's some length expanding circuit. And your goal is output some string that is not in the range of the circuit. So I want to stress, at least in this setting of parameters, this is like a huge number of valid outputs. There's 2 to the n to the 100. I guess when n is 2, this is like greater than the number of the atoms in the universe or something like that, minus 2 to the n. So there's a huge number of valid answers. Are there any questions about this? Okay, cool. So this is a total function problem. There'll always be an answer. Can anybody give me an algorithm for this? Okay, so you don't have to think very hard. Some people exactly. Very good. And depending on how you define FBPP, which is a function version of BPP, this means that like avoid is in FBPP. Okay, and this is like a really simple algorithm. You actually don't even have to look at your input really. You just need to know how many bits you're mapping to. Pick a random string. Boom, you've solved the problem. Okay, but that was really easy. Yeah. Can anybody give me a more advanced algorithm? And this is a good idea. Run I on what? Okay, all right, go come back to this. Algorithm. Okay, avoid as an FBP. Okay, all right. Let me make the task simpler for you. What if we talk about like AC0 circuits? Let's say this is an AC0 circuit, maps n bits into the 100 bits. Now you want to find something that's not in the range. The truth table of parity? I don't think so. I could just hard code it. Yeah.
Hit it with a random restriction, simplify it to a decision tree, and then just see, oh, it's a family decision tree. So
you can do this. You'll get some savings. You get a little bit of savings, but actually, you're not going to get very much savings off of brute force by doing this. And in fact, even for NC0 circuits, we don't have a better algorithm than this. If you go down to NC0 circuit, an NC0 circuit means every output depends on a constant number of inputs.
Constant is greater than 100.
Right. Yeah. Okay. There's this caveat, okay. Or okay. Let me not get into this too much. But for general NC0 circuits, okay, this is what we know or what we knew.
Sorry, the FBPP, what is the definition of the functional BPP?
Yeah, good question. I won't answer that. It depends if you ask Ryan or Scott, I guess. Or if you ask ChatGPT, which I guess Scott did. Anyway, this is a story. You can ask me if you're interested. Okay, so there's an FBPP algorithm, whatever that means. What's the first question you would ask? Is there a deterministic algorithm for this? Okay, who thinks that there should be a deterministic algorithm for this? Raise your hand. Oh, efficient. Yeah, I guess there is. Raise your hand if you think that there should be a deterministic algorithm for this. Okay, good. And good. And who doesn't think there should be a deterministic algorithm for this?
I don't think I know it.
Okay, good. So the audience seems to be mixed, which I think is good. Reflected, at least there's this quote from Renwing and Santanon. It is unknown whether a void in function version of NP or function version of P is implied by any plausible assumption. We're not even sure what the ground truth should be. So this is an open question in derandomization. Hopefully I'll tell you a little bit about how you can use obfuscation to try and understand this question. So this is kind of like the first question. And moreover, this question, it's interesting in itself. Okay, here's a natural problem. Can we solve it deterministically? Oh, okay, I forgot about this. I want to give you guys a puzzle. Are there things in FBPP, whatever that means, that are not in FP? Like okay. Yeah, Russell.
So this is actually due to some like internet troll who was giving me a hard time, but just picking a small random string.
Yes. So
depending on how you don't define FP.
Yeah, exactly. So here is a task which is solvable with randomness, which is not solvable deterministically, which is output a Kolmogorov random string. And this isn't like time bounded or something, anything like that. this is like the regular Kolmogorov complexity, which is like an uncomputable notion. It turns out that like there's no way to generate these things deterministically. So depending on how you define FPPP, which is why it's like a somewhat controversial thing, this is an example of a problem that can be solved with randomness, but not solved deterministically. But of course, it's like related to some uncomputable notion. But this tells you maybe, okay, you should be a little bit cautious about, I have a randomized algorithm, what can I get a deterministic algorithm? Is the question? Oh.
Yeah, you do diagonalization to say it's not in FP.
Can you do diagonalization to say that what is that? Oh, avoid is not an FP?
Avoid algorithm into itself.
Okay, I'm not sure. Well, we could talk about. I'm not sure what the. I don't think so, but maybe I'm not understanding what you're saying. But we can come back to it. Okay, so deterministic avoid algorithm. You know, it would. It's interesting for its own curiosity, but let me ask you. If you had a deterministic avoid algorithm, could you do anything interesting with it? This is for anybody in the audience who doesn't already know the answer. Maybe what could you get if you had a deterministic avoid algorithm? Does anybody have an idea?
I'll feed it to itself.
You feed it derandomization, yes, but actually I think you'll get something even more powerful. You'll get a Fields medal, and actually even better than a Fields medal, you will get $100 owed to you by Paul Erdős, which is I don't know. It depends what you care about, but so it turns out the deterministic avoid algorithm, exactly as you've all pointed out. Gives you breakthrough explicit constructions in combinatorics. In particular, there are these various tasks. I don't even want to tell you really what they are, but
The Erdős's notion of explicit was the same.
Okay, whatever. This is the $100 Erdős problem, which is construct explicit Ramsey graphs, other thing like rigid matrices, randomness extraction. Anyway, there's all these various objects in combinatorics. If you have a deterministic avoid algorithm, then you can actually construct these things. And this is something we don't know how to do. This is kind of a deficiency in complexity theory. We don't know how to, we don't have an assumption that says, oh, if this is true, then we can construct Ramsey graphs or explicit Ramsey graphs. We do know you can construct a small list of objects, one of which is a good Ramsey graph. You know, we don't know, okay, this thing is going to be a good Ramsey graph.
So how do you get strongly explicit graphs?
I mean, I don't know, it's Oliver's papers, that's what he says. So.
Yeah, but how do you get it from deterministic avoid strongly explicit?
I mean, it's Oliver. Oliver says, okay. I mean, I don't know what his definition of. Yeah. Okay.
But what is deterministic avoid? I mean, does it count if you have a list that one of which?
No, it does not. It's precisely a deterministic algorithm for this problem. You only get to output one, which is why it's different. Yeah.
When you say explicit hard truth table, it just means some kind of lower bound, but explicit languages are not.
It's like some hard functions in E. Yes, in E. Like hard truth table. Okay, it's an E.
E is not.
E is not. Oh, but if you want to write down a truth table, it's length 2 to the n, right? So if you want to produce it. It's probably what you will mean by it. Okay, but because you can't have a circuit for something that doesn't have small circuits, right? Okay, anyway. All right, so that's another topic. I've covered derandomization. I'm going to summarize these questions again, so you don't have to hold them in your head. I just want to point out that these are different topics, so like you shouldn't be looking for connections between them. Here is another field of theoretical computer science. It's bounded arithmetic. It studies logic. It's interested in, okay, if we have certain axioms, how hard is it to prove certain statements? What is like the length of the shortest proof to prove certain statements? And there's this kind of open question that's been open for about 20 years. This is a question Jan Krajcek asked. In fact, if you're familiar with proof complexity, he was interested in, he defined proof complexity generators, whatever that means, in order to try and answer this question, which is, does some proof system, PV1, prove the dual weak pigeonhole principle? So PV1 is just some logical system. We won't really care about it for this talk, which corresponds in some sense to polynomial time reasoning. So Steve Cook defined it And it's reasonably powerful. It can prove the PCP theorem. And the dual weak pigeonhole principle is sort of like a logical statement that's related to a range avoidance. It says, if you have n pigeons in 2n holes, there's an empty hole. It's like the lonely pigeonhole principle. And the motivation for this question is kind of like one of the fundamental questions in proof complexity is can you prove lower bounds efficiently? Like, is there efficient logic which lets us show that like statements related to p not equal to np? And somehow this is kind of like a first step to showing this, or at least this is the ideas, at least along one line of research. You can view the dual weak pigeonhole principle as like a baby version of trying to prove the hardness of proving lower bounds. So, okay, just to summarize, I've told you about 3 questions in 3 different areas of theoretical computer science. These questions are related to each other. Derandomization, is there a deterministic algorithm for range avoidance? Combinatorics, can a complexity assumption, in particular the range avoidance thing, imply explicit constructions? And something about logic, are there efficient proofs of the dual weak pigeonhole principle? These are the questions. My goal in this talk is to make you understand what the context of the questions are. So that's what I'm shooting for. And so in this first result, which is joint work with Jiatu Li, who is an undergrad at Tsinghua and will be a grad student at MIT, and Ryan Williams, who's here in the room, can show under plausible assumptions. I'm going to tell you what they are in a second. Actually, there's no efficient deterministic algorithm for void, and PV1 cannot prove the dual weak pigeonhole principle. And in fact, this gives, if you're interested in proof complexity, kind of the first separation of like, this somehow corresponds to efficient deterministic reasoning, and depending on who you ask, this corresponds to probabilistic efficient reasoning. These 2 notions are actually kind of separated under these assumptions. Okay, so I've said a lot of stuff. My goal next is to give you one nugget from this proof. But are there any questions? Comments? What? Oh.
Both of them, not or.
Both of.
It's an end.
Oh, under plausible assumptions. Yes, both of them. Okay, good. Okay, so now let me try and give you a nugget. And so let me ask you, what do you think? I've told you now that this problem is hard to solve deterministically. What might be a hard instance of a void? The title of this talk is a hint. Does anybody have an idea?
Universal privilege that can emulate the algorithm. Like the black box impossibility for VB.
Ah, okay. Maybe this is.
We actually find the circuit that like tricks that algorithm.
That's interesting. Maybe this is related to what you were thinking about. This is not the direction I was thinking in. Maybe we could talk later, and maybe there's something interesting there. But was there another suggestion?
PRF, PRG.
PRF, PRG. Oh, so you're saying okay, what if we have a PRG? Should this be a hard instance of a void? Is that what you're saying? Actually, this is a very good intuition. In fact, this is a major conjecture in proof complexity. This is this thing called like proof complexity generators, which basically says that for natural PRGs, it's hard to prove that something's not in the range of the PRG. In fact, since like Razborov has been championing this for a long time. Okay, this is another good idea, but how are you going to prove the security of that? Maybe you obfuscate the PRG. This is also a good idea. How are you going to prove the security?
You start with specific PRG, right?
You start from PRG, specific PRG. Okay.
When we function to PRG, then
Yeah, these are all good ideas. I was thinking of a different attempt 1, so I'll tell you that different attempt 1, which is what about a random point function? So you pick some random x star, you pick some random y star, you obfuscate the function that's y star and x star, and it's 0 otherwise. You could hope, if this obfuscation is really a really good obfuscation, that it's hard to actually print something that's not y star. Did the intuition for that make sense? Unfortunately, okay, I have no idea how to, or at least a priori, I have no idea how to prove this because, okay, almost all even if you had BBB here, like there's a randomized algorithm for this, right? Like, how are you going to use your assumptions to distinguish between a randomized algorithm existing and a deterministic algorithm existing? It's not clear how to do it. So here's the nugget. Oh, are there any comments before I
The algorithm inside.
put the algorithm inside?
Inside the obfuscation, see what it does.
So you're saying, okay, I have an algorithm for a void, and then I obfuscate that, and then I run a void on its.
Why I mean, you're increasing, but maybe.
Okay, I don't know how to make this work, but we can talk about it. Maybe there's some, yeah.
Sorry, it's just.
Yeah.
Rahul, just a question. Are we specifically talking about circuits or Turing machines?
Circuits. We're specifically talking about
I think
circuits.
that circuits would kill the
Oh, the
thing itself,
recursion.
right?
Yeah, okay.
Because otherwise,
Otherwise-
it seems like it's simple, right? It looks simple. But
I see. Yeah, we're specifically talking about circuits here.
okay.
Okay, so this is attempt one. Yeah, I don't know how to prove this a priori. So the kind of the nugget is add another assumption. And this is an assumption that's not cryptographic, that NP is not equal to coNP. And then instead of obfuscating a point function, you look at something that's kind of related to witness encryption. You say you have some arbitrary set instance phi, you pick a random y star, and now you obfuscate a function which is y star when the formula is satisfiable and 0 when it's not satisfiable. And it turns out, okay, there's work you have to do. But this actually, you can prove is a hard instance, at least some of the time, under this NP not equal to coNP assumption. So this is the nugget I want to convey. And, I think it's interesting, the idea of combining like a worst case complexity assumption with these cryptographic ideas, and hope maybe it can be used somewhere else. Yeah, so what you say is, yeah, there's a separate instance for each phi. I guess like what you really want to say is, okay, a hard unsatisfiable instance, but I don't want to define it like a hard unsatisfiable instance. So you can imagine. I want to say there's no algorithm which is always output something that's not y star for all phi for all of y star. Okay, hopefully I didn't. Did this make sense? Yeah.
The phi instance is chosen. I mean, how is phi chosen? Sorry.
Yeah, how is phi chosen? Okay, let me tell you what the final theorem is. So you say, assuming sub-exponentially secure I/O, and assuming NP is not equal to coNP. Actually, if you want the second result, you need something slightly stronger than this, but basically the same. You can show that there's no efficient deterministic algorithm for a void. So actually, what the construction does, or what the proof does, is it says, okay, suppose you could solve a void on every instance of this form. So for all phi, then you can actually prove that NP is equal to coNP, assuming. But the nugget I want you to take away is combining I/O with this NP not equal to coNP assumption actually lets you prove some potentially interesting.
The point, I mean, I guess you don't want to say it, but I want to ask it anyways. The point
Sure.
is that if someone outputs y star on this obfuscation, then
Yes.
you know that the circuit is not satisfied.
We know that the
Or-
circuit is not satisfied. Exactly. Okay, so this gives you completeness. The harder direction is soundness, but if you think about that for a bit more, okay. But good, excellent.
So can you repeat what is the y chosen by random, y star? The previous step?
Yes, this is the thing that could be output by F. So you just pick some random y star.
Oh.
This is explain this. Okay. All right. So we can return to our three questions.
Sorry, how do you check this y star? How do you know if you got it?
How do you know if you got it? Sorry, how do you know if you got it?
No, that's the correct y star, not just something perfect.
Oh yeah, because this okay. Your end goal at the end of the day is to come up with an algorithm for
Oh, you know the y star in your.
yeah. So you want to prove that something is unsatisfiable, and so then you see, does there exist any y star such that it returns itself in that? Yeah. So you get it. You know it. Okay, so these three questions about derandomization, it turns out that, so this answer is no. For combinatorics, you're going to need a new idea. There are some new ideas for this. I think this is a kind of very interesting question, even from like a cryptographic perspective. It's about getting the right definitions and constructing a reduction. I think this is interesting. And then logic, the answer was no. So here are the questions. My goal is to convey to you what these questions are and the nugget. So hopefully I've done that. Okay. So now we'll move on to tails in average case complexity and metacomplexity. And here I'm going to be fairly brief because Alan talked about this result yesterday. So recently, Hirahara showed in CCC last year that there is some problem that if you can show it's NP hard, it would eliminate your heuristica. A natural question to ask is, okay, is that problem NP hard? No. At least this would show, at least this would show that the approach is sound. Should we expect that problem to be NP hard? Another problem in metacomplexity, something that I guess I asked a few years ago, was about hardness of approximation of MOCSP. So it turns out you can use obfuscation of relatives to answer both of these questions. So this is joint work with Yiji Huang and Hanlin Ren. Hanlin here? No, hey. In the audience, the answer to both of these questions is yes. It turns out that Hirahara's problem actually is NP hard if you assume the existence of indistinguishability obfuscation. This is not so interesting for the question of eliminating heuristica, because you can eliminate heuristica if you already have indistinguishability obfuscation. But this is kind of like an anti-natural proofs result. Like for complexity theorists, we're all sad about cryptography in some sense because you killed our approach for proving circuit lower bounds. But okay, this is actually saying, okay, at least towards eliminating heuristica, this problem is NP hard. In fact, we pretty much already know the reduction. We know if you take a candidate IO thing, if you plug that in, we have the reduction from SAT to this problem. Okay. And in the second case, Hanlin talked about this yesterday. The answer is yes. Yes.
Do you have any speculation on if you can get equivalence between crypto assumptions and NP hardness of Hirahara's problem?
Yeah, I think that's a really good question, actually. So Hirahara's problem is time-bounded Kolmogorov complexity, conditional time-bounded Kolmogorov complexity in the superlinear setting. You can show that basically witness encryption implies that this problem is NP hard. In the reverse direction, I'm not sure. It's kind of, yeah. I think it's really worth investigating whether there's a converse. In fact, Hirahara's result that he talked about yesterday, you can think of as kind of like a weak version of that in some sense.
Since you mentioned the Giacoles, you want to mention who Yiji is?
Oh, right. Yes. So Yiji Huang is undergrad at Tsinghua University, and is he? I actually
get Columbia.
He's going to be at Columbia. You'll be working with him, or yeah, awesome. That's great. Yeah, well, both fantastic undergraduates. Sorry, I should have said that. Okay, this is all I want to say about average case complexity and metacomplexity, but here are two more areas of theoretical computer science where IO says something about it. And so the last thing that I want to talk about in my remaining time is about differential privacy. And this is kind of where maybe I'll say the most. Okay, so what is my What is my time situation? When is it? Okay. So tails in differential privacy. Probably you all know what differential privacy is. In this talk, I'm not going to assume very much about it. So differential privacy is a notion defined by Dwork, McSherry, Smith, and it basically says, okay, you can release information about data with some security guarantee. And what's really nice about differential privacy is it's actually really a useful notion. It's widely used in the real world, from the census to iOS to Google, and so that's great. One thing that's maybe not so nice about differential privacy is that it can be a rather restrictive notion. It can be quite conservative, and this for many tasks there are lower bounds which say you can't get differential privacy with certain utility for a task, which is kind of annoying and kind of restricts adoption. Okay, so how could you make differential privacy more applicable? How could you get around some of these lower bounds? Well, let's look at the definition of differential privacy. Probably everybody knows this, but okay. You want to release information about data. The way that that's formalized is you have some randomized algorithm, which takes as input a data set. In this talk, I'll always just pretend the data set is over 0, 1 to the n. It can be generalized, and just spits out some information. So it's just some randomized algorithm. This is the way you release data. And then it has some security guarantee. For the talk, it's not so important what the security guarantee is. It basically says that if you flip any bit in the original data set, the answer doesn't change by too much. But looking at this definition, is there anything that stands out to you? Stands out to you and what could be relaxed? I've definitely, it's really hidden, I guess.
If you use colors, it would make it easier.
Yeah. So as you've all said, it's statistical right here. Okay, why you're asking about all powerful adversaries A. In the real world, these don't exist. So natural thing to define is computational differential privacy, which was basically defined in these two works. And the definition is pretty much what you'd expect it to be. We take this adversary A, replace it by a computational algorithm A. Any questions about this? Okay, so what's the main question? Probably the question that you'd expect. SDP here stands for statistical differential privacy, CDP stands for computational differential privacy. So if we change our notion from statistical differential privacy to computational differential privacy, can we do something that we couldn't do before? In particular, for these tasks where we have lower bounds against, can we bypass them using computational differential privacy? Okay, it's a very natural question. It's been, I think this is like open question 10.4 in Vedan's textbook. Unfortunately, at least as of 10 years ago, there's not even candidates for a separation between this. And in fact, most of the prior work has been more on the negative side. There are some positive results. So in the multi-party setting, as we heard about earlier this morning, you can do things. And this is because you can do secure multi-party computation. So this is, of course, it's a very interesting line of research, but it's not talking as much about the differential privacy as it's talking about parties coming together and computing things. And another work that's pretty interesting shows that if you care about efficiency, actually there is a separation between these two things. There are CDP mechanisms that are exponentially more efficient than SDP mechanisms for tasks for certain types of tasks.
For learning, right? For learning.
So my understanding is that this task, where you have the efficiency gain, is only on these kind of contrived tasks where you have to sign, output, signature kind of stuff. It's not very. Yeah.
What come up with the concept is there are learning tasks where you can learn inefficiently, come up with efficiently.
Right, but I don't know if that corresponds to the adversary being efficient.
No, it's not related to that. It's in the same style as it's also roughly by the same people.
The gap between computational and statistical differential privacy?
Yeah.
Okay, maybe we'll take this offline.
The same question you were asked in the morning.
Yeah, but I was talking about this paper. But
Yeah, so what is the money?
I said that.
Take it off.
So, but my understanding is this is really for contrived tasks about kind of zaps and signatures and stuff like that. Maybe I missed something. Right. Okay, and so the negative results, I don't want to spend too much time talking about this, but we do know that the answer is no for low-dimensional tasks. There is a black box barrier saying that you can't base a separation just off of random oracles or collision-resistant hash functions or trapdoor permutation. And in fact, there's actually an approach based on Terence Tao and Ben Green's result about arbitrarily large or arithmetic primes and arithmetic progressions. That actually would, if you could extend it to multiple random variables, you could actually rule out any gap between CDP and SDP. So there is these results. And okay, let me just give you a toy question to work with first. Can you design a mechanism that it is computationally differential private, but not statistically differential private? Which seems like the question I just asked before, but there's a caveat. In fact, there's a really easy answer to this.
like see the output here.
Yes, exactly. Okay.
It's close to exact.
Okay, that's another answer. But yes, I'll go with this answer, which is because I wrote it up, right? There's a very simple mechanism which just outputs a pseudo-random string. Let's say if you have all zeros input, otherwise outputs a uniformly random string. To a computationally bounded adversary, you can't tell the difference between these two things, but a statistical adversary could. And so you'd be able to distinguish the all zero string from something with 1, 1 in it. But this isn't very satisfying because you're actually conveying no information here, right? Like a bounded party can't tell any information about D. So what you have to do is you have to define a task, a meaningful task with a utility or something like that. I'm not going to define it for you, but if you sat down and thought about it for 30 minutes, you'd probably come up with this definition. Okay. Any questions about this? Or?
So you're saying that the contrived example can follow these lines?
Yeah. So actually, the right question you want to ask is not, can we design a mechanism M that is CDP but not STP? You want to ask, is there a task?
Right, but I thought you said that there is a contrived task that can be based on that, or you didn't say that.
Oh, the contrived task is for a different question. It's about can you get things that you can do efficiently with a CDP, but
so you're saying that you cannot push this task level separation to contrived task. Sorry, you could not take the PRG example from the next time.
Oh, yeah.
No.
Yeah, I don't know any way to turn this into something. Well, okay, maybe if you squint at this, you might see. Okay, it depends. Yeah, I would say no. Okay, so what I want to tell you, so this is joint work with Badi Ghazi, Pajit Kamath, Ravi Kumar, and Pasan Manaransky. These are people at Google. Is that under very strong, but I would say plausible assumptions, and some of these assumptions are controversial. Actually, there is a task with a CDP mechanism, but no SDP mechanism. So I'll tell you what these assumptions are, but I want to tell you the nugget first, and that might lead you to the assumption. Okay, so this is an example where you can separate the two. And I'll tell you a little bit what the task is. Okay, so what's the first idea is, what might be a class of tasks that could separate at CDP from SDP? I don't know, does anybody have any ideas? The hint is the title and maybe even the program we're in. Anybody have an idea? So the idea is, what if you have a task where what you're outputting is a circuit? So this is like a meta-computational thing. You want a differentially private algorithm that outputs an algorithm or a circuit. So this is the class of tasks that we kind of are investigating, where you have to actually output a circuit. Yes, you could think of it as you could think learning would be an example of this thing. Good idea. So the specific task that we're interested in is something called, I'll call the n to the 0.99 distance problem. This parameter n to the 0.99, it's not so important. Don't worry about it too much. It just needs to be like little o of n. It's the following task. You're given some string D, and your goal is output some circuit that accepts D, but rejects all strings that are far from D in Hamming distance. You might wonder, okay, why am I just accepting D? Why can't I accept other things that are around D? Okay, that's fine too. This is maybe the simplest thing you could do. So your goal is, you're given a data set. I want to output a circuit that kind of tells me, am I near the original data set or not? And it turns out you can show that there's no SDP mechanism for this as long as your distance is like little o of n. So now the goal is, okay, can you find a computationally differential private mechanism? And if you're familiar with obfuscation, then you might first aim for a relaxed goal, which is, if I only consider adversaries that don't use C in a white box way, they only run the circuit C on specific inputs and look at output pairs. So this is can you find a mechanism that's secure against adversaries with black box access to C? This is like a weaker thing. And then if you can accomplish this relaxed goal, obfuscation could hopefully bring you from the relaxed goal to the CDP mechanism. So that's the approach I'm going to.
This is some promise problem, right? Then you have to
Is it a promise problem? I don't think, no, I think it's a total problem. I'm saying the guarantee that it needs to satisfy is promised. There's a gap in it, but it's a total problem. Does this make sense? Is there any questions? Yes, Russell?
So why is it difficult for STG? Because so
the type.
you can, okay, so just information theoretically, the fact that you're outputting a circuit doesn't really matter.
Yeah, it's just a set.
It's just like a truth, you could say a truth table, yeah. So why can't you say, oh, I'm definitely gonna output my string, whatever.
Yeah.
And then I'm just gonna like slowly fade off the probability.
Yeah, and so what you can show actually is that like pretty much the only thing you can do is like randomized response, where you like take a. Okay, maybe I don't want to get into the lower bound, but it turns out that by the way you fade out, you have to fade out like kind of centered around the point, and this is what's going to kill you. This is how you'll be able to like, depending on how you fade out, there's going to be kind of like a center point, or not really. Okay, but. Yeah. All right. I can talk to you about it later. Okay. Does anybody have an idea for how you might get a mechanism secure against query adversaries? So you have this task. I want to output a circuit that accepts things that are close to D, rejects things that are far from D, and I want to make sure if you only make a polynomial number of queries that you can't tell whether I started from D or D prime.
So how many number of queries to the circuit?
Polynomial number of queries to the circuit, right? With a function computer base.
Again, if I ask specifically about a point, you're supposed to accept it.
If you ask about a point, you either will say yes or no. It will output a circle output either.
No, but if it says in D, you're supposed to accept it.
If it's D, you're supposed to accept it, yes.
Can I output a randomized circuit?
Let's say no, but maybe you can. If you okay, so
you
yeah.
can output a distribution of circuits.
Can you output a distribution? Well, I guess if you had a distribution of circuits, then
I mean, your output algorithm is random.
yeah, output algorithm. Okay, so it seems like nobody yet has an idea, which I don't either. If you have an idea, this is like a very nice, this is just a question in query complexity, right? Like, you know, can you output a set such that if you make a polynomial number of queries for it, you know, you can be differentially private. So this is just a query complexity question. I don't know how to answer it. I actually think that this should be a question that should be answerable, but I don't know how to do it. But you can show, interestingly, or maybe at first not so interestingly, that there is a mechanism secure against non-adaptive query adversaries. So if the query adversary isn't allowed to make adaptive queries to your circuit, then you can be secure. And so here's the final nugget I want to convey. You know, what I've told you is that there is a mechanism that's secure against adversaries making non-adaptive queries to C. Originally, the plan was use obfuscation to turn this into a mechanism secure against adaptive Turing machines or circuit adversaries. So the natural way to do it is to take C and obfuscate it. That was the original plan, pretty much. But this, you know, obviously won't work, except that it kind of does. Because the reason why it obviously shouldn't work is that like here you have security against adversaries making non-adaptive queries to C. After you obfuscate it and hand it to an adversary, you know, they can make whatever queries they want to it. They can make adaptive queries to it. Obviously, it won't work. Anybody have an idea for what might make it work? I mean, you have to do a trick, obviously.
Randomize when you make a query, you kind of randomly reinterpret it.
Yeah, this is, I mean, well, okay, something along those lines. So the idea is you actually have to combine your original mechanism with keyless collision resistant hash functions and deferring inputs obfuscation. So there's some way to actually use keyless collision resistant hash functions to force the adversary to be non-adaptive. Keyless collision resistant hash functions, you know, I haven't told you what they are, but morally what they do is they say anybody who knows that something that hashes to the 0 string needs to have memorized it. Somehow this is kind of like being non-adaptive. And deferring input obfuscation is something we need to have our mechanism play nice with this thing. And actually, interestingly, it's like specific type of DIO that we need is like, seems to be like much weaker than like almost any other application of DIO that we've seen. It's like secure even with no auxiliary input, even in like a public coin sampleable thing. So it's kind of, anyway. And so it turns out what you have to do is you have to modify the problem where you will only consider data sets which hash to 0 under the hash function. And there's a lot of details to go through, but the nugget I want to convey is you can do this kind of surprising thing, which I think should have more applications, which is you can turn a non-adaptive query separation into something that's kind of adaptive, which seems at first to be not make sense, but you can actually do something. And so thanks for listening. The summary of this talk is like, we have obfuscation, there are these questions in these various areas. I think, there should be more applications of obfuscation, and yeah, thank you very much.
Really enlightening talk, and yes.
So I still don't get how it is what you were suggesting with the type of result you were after, how it differed from Ban and Zandri. The result of learning it's hard, things that are hard to learn. You can learn if you don't care about privacy, but you cannot learn. You can learn inefficiently if you do care about privacy. You can learn efficiently if you care about privacy.
So I'm not so familiar with this paper. Maybe we can look at it.
It's not, I mean, he's interested in the distinction between computational privacy and statistical privacy. They're doing no privacy versus statistical privacy.
So you cannot get oh, you're saying so there is. You're saying there is no computation. Okay, that's the point.
There's no privacy.
No privacy period. Okay. Very good.
Okay, so the last